Welcome to individual session 2 of MMED 2021. I'm going to be presenting on hidden assumptions of simple compartmental ODE models. In this lecture, I'm going to present on some hidden assumptions of simple compartmental ODE models. The goals for this lecture include to review the main uses of applied epidemiological modeling, to introduce our conceptual framework for applied modeling that we use at ICI 3D, to review commonly overlooked assumptions that are inherent in the structure of simple compartmental ODE models, and to discuss when these assumptions might be problematic and when they might be desirable, and to begin to explore some alternative model structures that relax the assumptions. First, I'm going to start by defining applied epidemiological modeling. By epidemiological, I mean related to the distribution and determinants of health-related states and events. By modeling, I mean the use of simplification to represent the key components of something you're trying to understand more clearly. And by applied, I mean for application to the real world. These are 5 main uses of epidemiological modeling that we use within the context of public health. And I will summarize these as insight, estimation, prediction, planning, and assessment. Under insight, I'm including both aspects that improve the understanding of the underlying dynamics of disease and health, as well as translation of results into decision-making and communication tools. By estimation, I'm referring to improving measurement and interpretation of key health indicators at the population and individual levels. By prediction, I mean projection and forecasting of expected future trends. Planning includes guiding study design and intervention rollout, as well as informing decisions through analysis and comparison of policy options. And lastly, assessment means evaluating the impact of public health interventions and assessing risk of future public health events. I'm now going to move on to introducing our conceptual framework for applied modeling. So this diagram here represents the ICI 3D approach to applied epidemiological modeling. We're creating what we call a model world that allows us to manipulate assumptions about the underlying dynamics. We then take this conceptual model world and implement it as a formal mathematical model, which we can use to gain a deeper understanding of how different processes lead to different outcomes. And finally, we take our understanding of the model world and use it to interpret things about the real world. A model world is an abstraction of the world that is simple and fully specified, which we construct to help us understand particular aspects of the real world. And a mathematical model is a formal description of the assumptions that define a model world. We know exactly what assumptions we've made, and we can follow those assumptions to their logical conclusions to address a research question. So this is the SIR model world, which you should now be familiar with. SIR model world can actually be expressed as many different models, and we'll see a number of different models throughout the next couple of weeks. I'm just going to give a brief overview now of some of the models that you should be looking out for. So we discussed yesterday the differential equation model, which most people think of as the SIR model. And these are the equations that we use to represent the ODE formulation of the SIR model world. We can also describe the model world in terms of what's known as a Reed-Frost model, which Becky will introduce you to later on, and the stochastic Reed-Frost model, which is a different implementation of a very similar set of underlying assumptions. We also have the chain binomial model that will be covered in the session on simple stochastic models. And the underlying equations are given here. So all of those are examples of different models that fall within the SIR model family. different assumptions that we're breaking down. So before we move on, I want to review what's meant by a compartmental model. A compartmental model is a model that partitions the population it represents into types and treats all individuals of a given type as identical. For example, in Steve's introductory video lecture, he introduced the basic SIR model. The equations he showed you were ordinary differential equation implementations of the more general model structure represented here, which I referred to earlier as the SIR model world. This model world describes individuals as susceptible, infectious, or recovered, and shows the processes that allow individuals to flow into, out of, and between these states. By writing the equations down as ordinary differential equations, we made a number of additional assumptions that weren't explicitly discussed. So I'm going to move on to review some commonly overlooked assumptions that are inherent in the structure of simple compartmental models. I'll then move on to discuss when these assumptions might be problematic and when they might be desirable. This might be a good time to pause the video and come back in a few minutes. Okay, I said that we were going to review commonly overlooked assumptions that are inherent in the structure of simple compartmental models. The first of these assumptions is the continuous treatment of individuals. This is really an assumption that the population is large enough that you can ignore the random fluctuations that are induced by the fact that individuals are discrete units, and instead you can think about the average system behavior. We can think about the continuous treatment of individuals as describing averages, proportions, or population densities. But sometimes, especially when populations in one or more of the compartments is small, we're interested in the variation in outcomes that results from the fact that individuals in the real world are discrete entities. This type of variation is the result of what's known as demographic stochasticity, which really just means randomness or noise that's introduced by counting individuals as whole numbers. In this figure, which comes from a paper that Becky wrote as part of her PhD, we're showing how demographic stochasticity can have an influence on the trajectory of an epidemic. So what we're seeing here is the number of infected individuals through time for 3 scenarios that have different population sizes. The black curve represents the differential equation model output, which, as you can see, is deterministic, meaning that for a given set of initial conditions, you always get the same outcome. In contrast, if we represent individuals as discrete entities, we get variation in the outcomes across different runs of the same model. And as you can see, as the population size increases, the trajectories of the model look more and more like the average system behavior described by the ordinary differential equations. Compartmental ordinary differential equation models also assume that you could ignore any other source of random variation that might produce variability in the outcome. One such example is what we call environmental stochasticity. So we know that lots of things vary with, for example, temperature. And this plot is showing the average daily temperature in Key West, Florida in 1993, which of course varies substantially throughout the year and even on smaller timescales. Depending on your research question, you might want to incorporate this type of variation into a model. So we've seen so far 2 of the major assumptions that we are making when we use compartmental ODE models. The first is the large population size. The second is deterministic progression, that for a given set of initial conditions and parameter values, a deterministic model always gives the same outcome. These assumptions make compartmental differential equation models relatively easy to work with. So one can relatively quickly determine what the model outcomes are, and how the outcome is determined by the parameter values and the initial conditions. This is a really, really useful property, for example, when you're conducting a sensitivity analysis. However, breaking these assumptions is often necessary, particularly when your research question focuses either on small populations or on understanding variability in the possible outcomes. However, breaking these assumptions is often necessary, particularly when your research question focuses either on small populations or on understanding variability in possible outcomes. In Becky's session on stochastic models, which track B will see today and track A will see later this week, she'll cover several modeling options that will allow you to modify these assumptions. The next several assumptions I'll talk about that are inherent in the structure of simple compartmental ODE models relate to the way that we treat time. To illustrate these points, I'll use an even simpler ODE model with only one compartment representing the population and two processes: birth, by which individuals can move into the compartment, and death, by which individuals are removed from the compartment. These are the processes by which the state variable, or the number of individuals in the population, is updated through time. In this model, time proceeds in a continuous manner, and the per capita birth and death rates do not change. This means, for example, that the model explicitly assumes that whatever's happening at 3 a.m. is the same as what's happening at 3 p.m., and whatever's happening in summer is exactly the same as in winter. For many processes, this is of course not a good representation of reality. And again, depending on your research question, these assumptions may or may not make sense for your model. Luckily, breaking this assumption is relatively easy. This is what the differential equation version of this model looks like. It can be simplified further by writing B minus D as R, a quantity known as the instantaneous intrinsic population growth rate. This equation can now be solved analytically by integrating from some time t to a future time t plus delta t. Doing this gives us a natural way to move between a differential equation formulation of the model and a discrete time formulation that allows you to represent processes that vary in time, such as seasonal birth and death processes, by averaging across temporally varying parameters for some specified delta t. Most often overlooked in infectious disease modeling, and one that can have important consequences for epidemic dynamics. This is the assumption of memoryless processes. A memoryless process is one where the waiting time until an event occurs doesn't depend on how long it's been since the last event occurred. Again, I'll use an extremely simple model to illustrate the point, this time with a single compartment and a single process by which individuals leave the compartment. This could be thought of as death. Again, we can understand the implications of this assumption by integrating the differential equation that corresponds to our very simplified model, this time from the initial time 0 to an arbitrary time that we'll call tau. We can now divide both sides by the initial population size to calculate the proportion of the population that survives at least to time tau. Looking at the shape of this curve, you can see that under this assumption, most individuals will leave the compartment very quickly, and a small proportion of the population will remain in the population for a long time. The distribution of times until an event occurs is known as a waiting time distribution. And the waiting time distribution for an event that occurs at a constant per capita rate, such as in this example, is known as an exponential waiting time distribution, for reasons that should be clear from the equations. Again, this assumption is often violated in reality. Here I'm showing an example of waiting time distributions based on data from a pneumonic plague outbreak in India. In this case, we're looking at the incubation period distribution. I've fitted two types of probability distributions to data available on the time from exposure to symptom onset for 30 people who were identified as cases during this outbreak. The gray curve shows the exponential fit to the data, and the green curve shows the best fit gamma distribution, which has a mean of 4.5 days and a shape parameter of 2.3. The gamma distribution is a much better representation of the actual distribution of the data. But as we've seen, simple ODE models implicitly assume exponential waiting time distributions. We'll talk more about the assumption of memoryless processes and ways to break this assumption during Thursday's interactive session when we do the tutorial on HIV in Harari. So in summary, simple ODE models are important tools for building understanding. It's possible to understand how all of the parts interact to drive average system behavior, especially for large populations. For example, we can calculate analytically what proportion of the population needs to be vaccinated to prevent an epidemic, and use this to develop an intuition for why some infections are easier to eradicate than others, as we saw in Steve's video lecture. Also, it's important to recognize the assumptions built into these models. When populations are small, average behaviors can be misleading. As we saw in the dynamical fever tutorial yesterday, outbreaks of a given disease tend to be either large or small without a lot of intermediate outbreaks. In this context, the system behavior is not well characterized by thinking about the average epidemic size. In addition, when rates vary, simple ODEs can fail to reproduce important observed dynamics. For example, the 2 yearly cycles that were seen in epidemics of measles in London throughout a large part of the last century. Another example comes from the temporal trajectory of HIV prevalence, which Jonathan will discuss in his lecture on heterogeneity. Later in the week, we'll see examples of how to develop models where the rates vary through time, or between individuals, or even with the time spent in a compartment. And then lastly, the applied epidemiological modeling process requires 4 basic steps. First, we have abstraction, where we take what we know about the real world and formulate a model world that we'll use to address a research question. The second step is specification and implementation of a formal model that describes the model world. We use this formal model to gain an understanding of the dynamics and to understand how our assumptions relate to the outcomes that we see. And finally, we translate our findings about the model world back into the real world to address our research question. That's the end of this lecture. Thanks for listening.